Hey, you guys, here's your first installment of Chapter 7. Now, Chapter 7 can be my favorite chapter, but it's also kind of my least favorite chapter. And I think that's because it's really hard, as for me anyway, to understand all of the stuff that they're trying to condense into such a small amount of time or space within the chapter. But either way, I still find it very interesting and find it a lot of fun to continue to understand quantum theory. Now, you may have heard of quantum theory before, you may not have, but either way, what we're going to be learning about is quantum theory and the electronic structure of atoms. Now, the electronic structure of atoms is basically talking about what are the electrons doing in the atom. Well, that seems like a pretty simple thing, but at the same time, it's not. I mean, we learned that there was a nucleus, and then we've learned, you might have seen this symbol for an atom before, but that's not necessarily true. I mean, these are kind of like orbits around an atom, and the orbits kind of indicate that the atom is like the nucleus is like the sun, and then the atoms are like a planet. But that's not really, I mean, sorry, the electrons are like a planet, but that's not really the case. And we're going to learn about some different theories that talk about the electronic structure of the atom. So in this chapter, we'll be looking at what is light, how does it travel, and then how fast does it travel, and then looking at an electron and how it moves, and then also what the electron and light have in common. So in this chapter, if you look at, we have a neon sign being shown over here, and that neon sign is in this chapter because of the fact that there is a gas inside of these neon tubes inside here. And when you electrify them, the electrons move around. And when the electrons move around in between levels, then that, as they relax, the electrons relax back down to different states, there is an emission of energy. Now that energy was absorbed by the electrons to move them around from the electricity that this is plugged into. So that's one experiment that we're going to look at that has to do with the electronic structure of atoms. The other experiment that we're going to look at is the black body radiation. And this picture on the slide here of what looks like a heater, the heater is being heated up. There's a filament or an element or some type of material in there that is being heated up. And when it's heated up, it gives off light. Now, which type of light depends upon how hot it is, basically. So, and when I say type of light, we're going to be learning about wavelengths, and we're going to be learning about frequency, and we're going to be learning about the energy of those things. And then we're also going to be learning about what that light consists of. What we're going to learn about is photons of light that are little bits of light that have specific energies. So since this is something we can't see, just like atoms are and so on, but light is a little bit more challenging. We can't see it. Well, we can see light. We can see some forms of light, but we can't see what the electrons are doing. We just have to infer it from different experimental evidence, like these neon signs or this black body radiation. So let's get started here on quantum theory and the electronic structure of atoms. So before we begin, we want to talk a little bit about waves, because electrons and light travel in waves, but they also have particle nature as well, and that's what we're going to look at in this chapter. But first, let's talk about waves. Waves, as we define them, have a wavelength, which is peak to peak or trough to trough. They have an amplitude, which is the height of the wave or intensity of the wave, I like to call it, from the midline, with the midline being this, or direction of propagation. So this is also an intensity. You can have an intensity below the wave, below that midline or direction of propagation, or above. To compare different types of wavelengths of different frequencies and wavelength, you can have a wave that has a long wavelength, or a wavelength that has a shorter wavelength. Now these wavelengths are measured in meters. Now, as far as measuring in meters, you can measure in meters, but a lot of times wavelengths are really small. So we will use things like nanometers, or even picometers if you want to. And then when we do bond lengths, we'll use what's called an angstrom. So there's all different units, but those units are related to the meter. And since they're related to the meter, they'll have a conversion factor using our metric conversions like we were doing before. So let's just do a quick, some fast fill-ins here. Wavelength, that is the distance between points on a successive wave, and that's what I was circling up there. Amplitude is the vertical distance from the midline, and then frequency is the number of cycles or waves that passes a particular point in 1 second. So on the wave picture above here, this bottom one has a higher frequency, so more cycles pass per second, and then the top one does. And a hertz is it's a name for cycles per second. So if I say I have a wave, a wavelength of light that has a frequency of, say, 300 hertz, that means its frequency is, you could also write it as 300 per second. 300 what? 300 wavelengths per second. Now the speed of a wave, and I wrote over it here, the speed of a wave, let me get rid of this stuff, is determined by the wavelength and the frequency. So here you'll see lambda times, looks like a v, and that's a nu. Wavelength times nu is equal to the speed of the wave. Now wavelength, in order to use this, your wavelength must be in meters, and your frequency or speed, I'm sorry, must be in per second. So when you end up with your speed, I messed that up, didn't I? I meant to say your wavelength is in meters and your frequency is in per second. So then when you multiply those two quantities, you get a speed, and that speed is in meters per second. So waves can have certain speeds. I mean, I guess even if you had water waves, right, you'd have, if you were standing at a vantage point and you measured those water waves, you could measure how long it took a peak to go by you or a trough to go by you, and then you could measure how fast that wave was moving. So I guess it would be like that even in water waves through the ocean. You know, when there's an earthquake under the ocean, it produces a wave of water that then moves at a certain speed, and that's how they know, they can tell people who are living, you know, on the coast to get out very quickly, because they can say it will be here in 3 hours, you know, because they could actually measure how fast it was going through water. So light waves, same idea, but a different method for measurements. So let's keep on talking about light. Now we're talking about light as a wave. Now originally, if you think back to Newton's time during looking at a prism and how a prism separated light wavelengths into different colors, it was kind of thought that light was continuous, and continuous just meant that you didn't have bits of it. So the wave nature of light was illustrated through Newton's prism, and I have a GIF on the next one that shows that you have light coming in and it separates that light into different wavelengths. So light, as far as behaving like a wave, Maxwell's equations propose that this visible light consists of electromagnetic waves. Now I have a GIF going here that shows the type of movement that an electromagnetic wave does. So a mechanical wave would be something like through a string. An electromagnetic wave does not need a media to transmit. So light comes to us from the sun through empty space, if you will. I mean, at one point, they were looking for an ether or something like that, that waves transferred through, and that wasn't found. It was never found, because if the idea was that if light was traveling through something, that it would slow it down, and it never did, no matter how you looked at it and whatever parameter, the light was traveling at the same speed. So this electromagnetic radiation is the emission and transmission of energy in the form of electromagnetic waves. Now, the electromagnetic waves that we're going to be talking about, and waves or lambda for that symbol, are things like visible, ultraviolet, infrared, things like that. So this speed, like I said, that was the same all the time, is 3 times 10 to the 8th meters per second. And that is a constant in a vacuum. So there is that same formula that we saw in the previous slide, but on the previous slide it was a U instead of a C. And that U was the speed of a wave. It could have been any wave, but this is C, the speed of light in a vacuum. And that lambda is in meters, and this frequency is in per second. So when you multiply them, you get meters per second. So as far as keep on going with electromagnetic radiation, we were just talking about and showed on the previous slide how that was moving through a vacuum. And electromagnetic radiation of different wavelengths and frequencies has different names. So an X-ray is a range of frequencies that has a pretty short wavelength and a pretty high frequency. When I say pretty short and pretty high, I'm comparing it to visible, or I'm comparing it to infrared or microwave. So down here is lower energy form of the waves, and up here is a higher energy form. So there's your visible, and that's showing that the visible light actually consists of a range. And there's your Roy G. Bibb, if you ever learned about the rainbow: red, orange, yellow, green, and then indigo and violet. And then if you go down a little further past the ultraviolet range, you will find, past the violet, you get ultraviolet. And if you go past the red, you get infrared. Infrared and ultraviolet we can't see with our eyes. There are certain insects and certain species that can detect heat, which is infrared, but we as humans cannot. I have another picture here that I like that shows the differences in wavelength in these electromagnetic spectrum. The gamma rays have a short wavelength and a high frequency, and then things like radio waves have a very low frequency and a long wavelength. So that kind of gives you an idea of the differences in the electromagnetic spectrum. And then our visibles right here in the middle. So as a little quick practice here, if we are going to utilize the relationship we just learned, if you have an electromagnetic wave that has a certain frequency in hertz, and remember hertz is per second, determine the wave's wavelength. So that's our relationship, that lambda time frequency is equal to speed of light. We're going to use speed of light as our constant, and we're going to rearrange to solve for lambda. So we were given the frequency, and the frequency is 3.664 times 10 to the 7th hertz. And then when we multiply that, we're going to get a wavelength of 8.24 meters. Now that's really, really long when you think of it, because here you have something like 8.24 meters, but from wave peak to peak or trough to trough. And the next question is in what region of the electromagnetic spectrum does that fall? Well, you would go back to that picture, which was a little snippet of it is over here, and that falls in radio waves. So this is 10 to the 7th hertz. So here's 10 to the 7th hertz, or looks like 8.24 meters. Now this is a wavelength here. This is nanometers here. So 10 to the 9th nanometers looks like it's falling right around here. So it's in radio waves. So on your fun sheet, you have a question here that's out of your textbook, problem 711, that's asking you to think about time, because time is measured in seconds. And what is a second? It's defined as this number. Now before, this is a new definition, I think, as far as time before that. This second definition is defined as, I don't even know, was 9. Let's see, this is million, this is billion, is this 9 billion? This is a huge number. Cycles of radiation in the cesium atom. Now cycles, what does that mean? It means you have an atom and it is undergoing radioactive decay. And when it undergoes radioactive decay, it does so many per second. Actually, it does so many in 1 second. Yes, that's what a second is. So if it's this many cycles or this many decays, radioactive decays in 1 second, and that can be measured by a detector on the other side. And that's how our second is defined. Now, given in this example, you're given cycles per second. So that is a frequency. So you can use your relationship of C equals lambda times the frequency to get the wavelength of that. And then just like we did on the previous problem, you can go ahead and look at the electromagnetic spectrum and then see what area that falls in. And then finally, I just ask you to draw a representation, how to label wavelength and amplitude. So here's your electromagnetic spectrum that you would reference to see where that is in the electromagnetic spectrum. And is it visible to our eyes? Now, if it doesn't fall within that tiny little visible spectrum, no, it's not. So once you solve for your wavelength, see what you can find there. So to continue on with getting a handle on quantum theory and what it means, this first mystery, your book puts them in kind of mysteries that were being solved in the early 1900s, very early 1900s. And one of them was this heated solids problem. And a heated solids problem, the physicists were looking at when you would heat a solid up, just like it was a light bulb filament, light would be given off. And supposedly the German government wanted him to determine kind of the most efficient light bulb. So he was studying light bulbs, and light bulbs, of course, are heated solids. So he was studying them, and this picture is not out of your textbook. Your textbook has something similar to this, but if you can see this visible range here, we just talked about electromagnetic radiation, and that when you would heat a solid, and if you look at this picture, you have a 3000 K, that's how hot it is, and you have a 4000 K, and you have a 5000 K. As you heat up a solid, and I guess we're assuming this is the same solid, if you heat it up, it starts to glow, and it starts to glow red. See the red right here? This is a red line. And then if you continue to heat it up, it starts to change color, and it glows green. And then it continues, you heat it up more, and it glows blue. And then eventually, I believe you continue to heat it up, and it will glow white. Now, in class, we will look at a PhET simulation about this that enables us to play with this a little bit to see what's happening. But Max Planck was looking at trying to solve mathematical equations to model these lines. And he couldn't do it with classical theory. The classical theory that of physics, particle physics that had been around for a long time was not fitting the data. So he threw it out, and he learned that when the solids are heated, they emit electromagnetic radiation. And he learned that the amount of radiant energy emitted by an object at a certain temperature, so you see that here, there's different temperatures, depends on its wavelength. So looking at this picture, this graph I have here, I have in words that energy and wavelength of electromagnetic radiation are related. What does that mean? So if we go down and look at this picture, I am going to remove these annotations here so we can see this a little bit better. If we look at this graph, on the x-axis, you can see wavelength. On the y-axis, you see what's called spectral radiance, but that's also another thing for intensity. This is from Wikipedia, I think. But it's another word for intensity or energy. So when wavelengths become shorter and shorter and shorter, energy increases and increases and increases. But there's this part, or radiance here, but this part, there's a part where it just falls off, which is kind of strange. And that's what Max Planck was having a problem with. So once he analyzed this and looked at the data, I still cannot find, there's an extra credit project for you if you wanted to, what is the data that he gathered, that he then found the formula that we are now going to see. Now what I have back here is, I'm going to take off my, what I have back here is a little GIF. I love to find GIFs, and GIFs are interesting because they're just a little tiny animation that helps you understand something, at least it does for me. And this is a small little fraction of the visible range, as you see on this graph. And it's showing when something becomes colder, it gets redder. And when something becomes hotter, it gets the bluer. So that's what you're seeing in this picture here in your graph. As something got hotter, it becomes bluer, and it becomes cooler, it becomes red, more red. So here's your wavelength on your graph here. You're seeing wavelength versus this B, and that B has to do with intensity or energy again. So as wavelength becomes shorter, energy or intensity becomes higher. So let's look at Max Planck's equation. Now, there's a much more complex equation that he has for these phenomena, but what we are going to look at is that energy is directly related to the frequency of the light. And that as that becomes shorter and shorter, this frequency becomes higher and higher, then the energy becomes higher and higher. And this H is Planck's constant. So let's continue on with this mystery number one, which is this heated solids. And here I have this little GIF of a light bulb, and that light bulb is flickering like a candle. But there's a tungsten filament, or there's some sort of filament in here that's being heated. So what Planck did was look at all that data, and his hypothesis was then that energy is emitted or absorbed in discrete quantum. And that quantum there must be some sort of fundamental constant that describes that level of particleness of light. And that's what he was seeing. Remember, they thought light was continuous. So that's where these equations come from, and I wrote that on the previous slide. And what this is showing, that the energy of a certain frequency of light is related to Planck's constant as far as it becoming more particle-like. So Planck's constant is this teeny tiny number, and this teeny tiny number is a fundamental constant of nature in that it describes light, and it describes the number of photons of light. So we are going to see another type of formula that Einstein proposed that had to do with the photoelectric effect. But here, as far as we're going to stop with, because we only have a few more slides on this mystery here, is that the energy of light is equal to or related to Planck's constant and frequency. And then you'll see this little n here in front of it here. And this n means the number of photons of that light. So what this is saying, if I have one photon of a certain light of, say, I don't know, 1 times 10 to the 10th inverse seconds, right? That is a frequency. There's going to be an energy associated with that, and I can calculate that based upon Planck's constant and this frequency. So the energy of 2 photons of light would be twice that. Energy of 3 photons would be 3 times that. So why this is fundamental constant of nature is because it takes it down to the particleness of nature. So there's that picture again that is describing the same thing. So let's work on our fun sheet. Fun sheet number 2 is talking about a human's eyesight, and that is actually more acute than a dog, but less so than a cat, because cat, as far as light detection, because a cat can really see fewer photons than a human can. But if a human can detect light of 600 nanometers of a wavelength with an energy that is associated, that is 5 times 10 to the 17th joules, how many photons of this light does this correspond to? So think about a human eye. You know, it's a human eye. Here's some eyelashes, and remember the pupil of the eye is actually a hole, right? So light can travel into it. I should have drawn that down here, but either way, imagine this light is coming off and going into there, and the light, say for example, is 600 nanometer wavelength, but there must be enough photons reach the eye of the human to the tune of 5 times 10 to the 17th joules. So how many photons would that be? So you can think about our equation that we learned. Now this is NHV. Now I want you also to remember that V is frequency, or nu. And recall that C is equal to lambda times nu. So if I want to have a different form of this equation, I can have E equals NH C over lambda. Did I do that right? Because let's solve for nu. C over lambda. So I did do it right. There it is, HC over lambda. And if there's an N there, of course, if that's 1 photon, then that would be one of them. But now in this problem, we have so many joules of energy that we need. So pop that in there and solve for the number of photons that corresponds to. And also to figure out what color it is, you can go look at that electromagnetic spectrum that we were looking at in our textbook that showed the different energies of light. And then I have a next question here. If the light is now 500 nanometers, should more or fewer photons be required? Now remember that the shorter the wavelength, a shorter wavelength has a higher energy. So shorter wavelength has higher energy. So it looks to me that this 500 is shorter than the 600. And if that's the case, then would you need more or less? That's your question for that. And then for fun sheet number 3, the question here is thinking about how molecules interact with light. Now, this is a PhET simulation here. And in this PhET simulation, you can go to this site and you can put a molecule in here, and then you can shoot it with different wavelengths of light. And what's going to shoot out of here is photons of light. And that's what these are. And when those photons of light hit the molecule, they can cause different effects. And one of those effects can be to break the bonds, or just to make the molecule vibrate. This is nitrogen, say this is a triple bond. It can make the molecule vibrate back and forth. And then depending, it can make it spin. Microwaves make water molecules spin on an axis. So there's all different effects of light on molecules. But what I'm asking you in this question is to go look at table 9.4. And table 9.4 is a couple chapters ahead. But what it gives is what's called a bond enthalpy. We already talked about enthalpy in chapter 6. So enthalpy is an H. Remember, that's associated with something. So for a nitrogen triple bonded molecule to be converted to 2 individual nitrogen atoms, there's an energy associated with that. And you can go get that from table 9.4. So, and recall, in table 9.4, if you look at that, you're going to get a value that's in kilojoules per mole. Now, that's a mole. That's 6.02 times 10 to the 23rd molecules. Now, when we're doing this type of problem, and it's a covalent bond, which is an actual molecule, that's an individual molecule, to figure out the wavelength, you might need to bring in Avogadro's number. So don't forget that, because this is in kilojoules per mole. You might need Avogadro's number to get the amount of energy in kilojoules or joules that is required for one molecule. And then you can utilize the E equals NHC over lambda. So give that a shot, because remember, it shouldn't be a huge number. And if you use kilojoules per mole, it's going to be a huge number. These energy values are small because they're on a per molecule basis. So that's your first installment of chapter 7. That's the first 2 or 3 sections.